This is Radhika. I'm going to give a video lecture on AC machines, subject code 18EE403C. So today we are going to discuss about the chapter is test on single phase transformer. This is the second chapter. In this we are going to discuss about the practical transformer with winding resistance and practical transformer with winding reactance. These are the two topics we are going to discuss today. So last class we discussed about the ideal transformer, transformer on no load, transformer on load, and a few problems on transformers on load. So in this last class we discussed about the ideal transformer. Ideal transformer means nothing but it is the no load transformer. So without any load has taken in primary and in secondary. An ideal transformer is one that has no winding resistance, no leakage flux, and has no copper and no iron losses. In other words, an ideal transformer consists of two purely inductive coils wound on a loss-free core. In practice, it is impossible to get an ideal transformer, but practical transformers have properties that approach very close to an ideal transformer. So that is the about ideal transformer and transformer on no load. So that is an ideal transformer is one that has no core losses and no copper losses, but in practice it is very difficult to get an ideal transformer when an actual transformer is connected to load. There is iron losses in the core and copper losses in the winding, means both primary and secondary. Whenever load is not connected on the secondary winding and primary winding is connected to AC supply, the condition is said to be no load condition of the transformer. So that is the no load on the transformer. So in case of load transformer, it has the secondary current. So there is the load and it has the current. So in a on load transformer, when the secondary winding of a transformer is connected to a load, the transformer is said to be on load. When transformer is loaded, a current I2 will flow through the secondary winding. The magnitude and phase angle of I2 with respect to secondary terminal voltage V2 will depend upon the characteristics of the load. The current I2 will be in phase with V2 if the load is resistive. It lags behind V2 if the load is inductive, and it leads V2 if the load is capacitive. So that is the transformer on load. So today we are going to discuss about the real transformer with winding resistance and reactance and phasor diagrams for the real transformer and transferring resistance from one side of transformer to the other side. So in transformer with winding resistance in ideal transformer there is no resistance in the windings, but in an actual transformer there is always present some resistance in the primary and secondary windings. The primary has a resistance R1 ohms, is called primary resistance, and the secondary has a resistance of R2 ohms, that is called secondary resistance, and the resistance causes copper losses and voltage drop in their windings. The resistance causes the flowing results in the transformer. So in this, in practical transformer has coils of finite resistance. The effect of resistance is to cause voltage drops in the two windings. Let R1 and R2 be the resistance of the primary winding and secondary winding respectively. Hence, the I1 R1 and I2 R2 represents the corresponding voltage drop in the windings. So here this is the diagram of transformer, practical transformer with winding resistance. So in this transformer we have the two windings, primary winding and secondary winding. In primary winding we connected with the R1 resistance, and in it has the I1 current and the turns in one, and it has the self induced EMF E1, and it has the supply voltage V1. In secondary winding it has the N2 turns and a mutual induced EMF E2 and the load current I2, and the resistance is R2 and the voltage V2. So this is the diagram for transformer with winding resistance. So here in this, the KVL equations for the primary and secondary loops, we have primary induced EMF E1 is equal to V1 minus I1 R1 voltage drop, and in secondary induced EMF that is equal to E2 is equal to V2 plus I2 R2. In primary induced EMF, E1 is equal to V1 minus I1 R1 and E2 is equal to V2 plus I2 R2. And here we have the phasor diagrams for different loads. So in secondary resistance, R2 causes a voltage drop I2 R2 in secondary winding, due to which the secondary voltage V2 is less than that of the secondary induced EMF E2. So here V2 is equal to E2 minus I2 R2 vector difference. Similarly, the primary resistance R1 causes the voltage drop I1 R1, due to which primary induced EMF E1 is less than that of the applied voltage V1. So that is equation minus E1 is equal to V1 minus I1 R1, that is the vector difference. The vector diagrams of the transformer with the resistive effect for a purely resistive load means unity power factor, inductive load lagging power factor, and capacitive load is the leading power factor. So that we will discuss about the phasor diagrams of resistive load and inductive load and capacitive load. So in this, when we are taking the resistive load, in this the V2 and I2 are in phase. So here the flux is common for both primary winding and secondary winding. So that's why we are taking flux in x-axis as a reference line, and the I0 is the no load current, and I2 dash is the transformer secondary current. It will affect in primary. So the resultant of I0 and I2 dash, that will be I1. The angle makes between I0 and V2 is pi naught, and I1 V1, the angle is theta 1. So the I2 V2 and E2 will be in y axis, and minus E1 is in a y axis. So the I2 dash will flow opposite direction with I2. So with so here minus E1 is equal to V1 plus I1 R1 from this diagram. So E1 minus E1 is equal to this plus I1 R1 and plus V1. So that is equal to minus E1 is equal to V1 plus I1 R1. So this is a phasor diagram for resistive load. In case of inductive load, this is the phasor diagram for inductive load. In this, the flux is the reference for both primary and secondary windings. So here in this, here in inductive load we are taking the lagging. So here V2 and E2 is in lagging. So E2 and V2 E2 and I2 makes the angle of theta 2. V2 I2 takes angle of theta 2, and here in primary in above side, here is the minus E1 that is equal to V1 plus I1 R1. But here in lagging side, V2 is the lagging of I2. So here I2 dash is opposite direction to I2. So this is the here is the lagging angle of I2 V2, and here this is the phasor diagram for capacitive load. Here in primary, that is equal to minus E1 is equal to V1 and I1 R1. So here I2 is leading. So here in this I2 dash will be flow with opposite direction of I2, and so I and in which direction I1 will flow, here I1 and R1 will be in same direction. So here also I2 in it will be flows in which direction, the I2 R2 will be in the same direction here. So here E2 is equal to V2 plus I2 R2. So this is the capacitive load for the transformer, winding transformer. So here next we go for equivalent transformer, sorry, equivalent resistance. So in this, in equivalent resistance with the resistance R1 and R2 in primary and secondary windings respectively, the resistance of one winding can be transferred to the other winding by using the factor K square. Here K is the transformation ratio. This means that both the resistances can be referred to either primary and secondary, which helps in finding equivalent resistance on either side. The advantage of transferring the resistances to one side is that it makes calculation simple and easy, because then we have to work in one winding only. So here in this, with the resistance R1 and R2 in primary and secondary windings, the resistance of one winding can be transferred to the other winding by using the factor K square. This means that both the resistances can be referred to either primary or secondary, which helps in finding equivalent resistance on either side. So the advantage of transferring the resistance to one side is that it makes calculations simple and easy, because then we have to work in one winding only. So here in this, uh, to model a transformer, it is important to understand how resistances or impedances are transferred from one side to another, that is primary to secondary or secondary to primary. Resistances or impedances transfer helps to calculate the current or voltage easier and get rid of that uh, ratio for the rest of the calculation. So the resistance of the windings can be transferred from LV and HV or vice versa on the basis of equal power losses, that is copper losses. So here it is referred to primary side and it is referred to secondary side. So in primary side, when secondary resistance R2 is transferred to the primary side, it is divided by K square, then it is known as equivalent secondary resistance referred to primary and denoted by R2 dash. So that is equivalent secondary resistance referred to primary R2 dash is equal to R2 by K square. So here when secondary resistance R2 is referred to the primary side, it is divided by K square, that known as equivalent secondary resistance referred to primary, so and is denoted by R2 dash. So equivalent secondary resistance refer to primary. So in primary side has the R2 dash is equal to R2 by K square. K is the transformation ratio. When the secondary resistance is transferred to primary side, then the secondary has no resistance. The resistance R naught 1 is equal to means in primary resistance, that is equal to R1 plus R2 dash. So that is the total resistance in primary side. So that will be R1 plus R2 by K square. So this is known as equivalent R1 plus R2 by K square is known as equivalent or effective resistance of the transformer referred to primary and is denoted by R naught 1. So equivalent resistance of transformer referred to primary. So in primary side the total resistance is R naught 1 is equal to R1 plus R2 dash. So in referred to in secondary, when the primary resistance R1 is transferred to the secondary, it is multiplied by K square. Then it is known as equivalent primary resistance referred to secondary and is denoted by R1 dash. When primary resistance R1 is referred to the secondary, it is multiplied by K square. Then it is known as equivalent primary resistance referred to secondary and is denoted by R1 dash. So equivalent primary resistance referred to secondary, R1 dash is equal to K square R1. So when the primary resistance is transferred to secondary side, then the primary has no resistance. So the resistance R2 plus R1 dash is equal to R2 plus K square R1 is known as equivalent or effective resistance of the transformer referred to secondary and is denoted by R02. So equivalent resistance of transformer are referred to secondary. Equivalent resistance of transformer referred to secondary. So that is R02 is equal to R2 plus R1 dash, that is equal to R2 plus K square R1. R naught 2 is equal to R2 plus R1 square is equal to R2 plus K square R1. So here, so in this the copper loss in the secondary winding is I2 square R2. This loss is supplied by primary winding current if I if I1 is the I2 dash equivalent resistance in the primary, which would have the same loss as with R2 in the primary. So then R2 dash, sorry, I2 dash R2 is equal to I1. So this is the copper loss. So I2 square R2 is equal to I1 square R2 dash. So from here R2 dash is equal to I2 square by I1 square R2. So that is equal to R2 dash is equal to R2 by K square. So where K is the I1 by I2. The R2 dash is called the secondary resistance referred to primary. So the total resistance of the primary R2 dash is the R0 2 is equal to R1 plus R2 dash. So that is equal to R1 plus R2 by K square. Similarly, if we uh, proceed in the same way, the equivalent primary resistance when referred to secondary is obtained. The total resistance of the secondary R naught 2 is equal to R1 dash plus R2. So that is equal to K square R1 plus R2. So this is the diagram of equivalent resistance referred to the primary. So here R naught 1 is equal to R1 plus R2 dash in primary side. Total resistance of the transformer referred to primary, and this is the total resistance of the transformer referred to secondary. So in secondary R naught 2 is equal to R1 dash plus R2. So this is the secondary. So here we can conclude that to transfer primary resistance to secondary side, multiply it with K square, that is R1 dash is equal to K square R1. To transfer secondary resistance to primary side, divided it with K square, that is R2 dash is equal to R2 by K square. So here in order to shift resistance from primary to secondary, multiply the primary resistance R1 by K square. So in order to shift resistance from secondary to primary, divide the secondary resistance R2 by K square. Hence, in general, any impedance transferred from secondary side to primary side must be multiplied by the square of the turns ratio is K square. So in practical transformers, factors need to be considered. The ideal transformer is not a sufficiently accurate model for all purposes. A better model should include winding resistances, leakage fluxes, effects of limited magnetic permeabilities of the core material, core losses, stray capacitances due to the electrical coupling between windings, significant at a high frequency. So next we go for leakage flux or magnetic leakage. So here in this, the ideal transformer model assumes that all flux generated by the primary winding links all the turns of every winding, including itself. In practice, some flux traverses paths that take it outside the windings. Not all the flux produced by the primary current links with winding, but there is leakage of some flux into their surrounding in primary. Similarly, not all of the flux produced by the secondary currents, means load current, links the primary. Rather, there is losses of flux due to leakage. These effects are modeled as leakage reactant in the equivalent circuit representation. Such flux is termed leakage flux and manifests itself as self-inductance in series with the mutually coupled transfer windings. So this is the magnetic leakage of transformer. So in this in this in case of ideal transformer, it was assumed that the flux produced by the primary winding links with both the primary and secondary winding, but in an actual transformer a part of the flux produced by the primary winding does not link with the secondary winding. Similarly, a part of the flux produced by the secondary winding does not link with the primary winding. So this is the diagram for magnetic magnetic leakage flux. A part of primary flux pi L1 not links with the secondary winding, and a part of secondary flux pi L2 not linking with the primary winding. So the two fluxes pi L1 and pi L2 leaks out of the core and do not link both windings. Hence, these fluxes are known as leakage fluxes. Hence, pi L1 is known as primary leakage flux and pi L2 is known as secondary leakage flux. So here in primary leakage flux pi L1, the flux which links the primary alone and does not link with the secondary is known as primary leakage flux pi L1. This flux is produced by the primary ampere turns I1 N1. So therefore it is proportional to the primary current I1 and the number of primary turns N1. The flux which links the primary alone and does not link with the secondary is known as primary leakage flux pi L1. This flux is produced by the primary ampere turns I1 N1 only. Therefore, it is proportional to the primary current I1 and the number of primary turns N1. Secondary leakage flux pi L2, the flux which links the secondary alone and not links with the primary is known as secondary leakage flux pi L2. So this flux is produced by the secondary ampere turns I2 N2. Therefore, it is proportional to the secondary current I2 and the number of secondary turns N2. So at no load, so the flux which links the secondary alone and not links with the primary is known as secondary leakage flux pi L2. So this flux is produced by the secondary ampere turns I2 N2. Therefore, it is proportional to the secondary current I2 and the number of secondary turns N2. At no load, the primary current is small and the secondary current is equal to 0. Hence, the primary and secondary ampere turns are small, therefore, leakage fluxes are negligible. But when the load is increased, Both primary and secondary windings carry huge currents. These currents increases corresponding ampere turns, which increases leakage fluxes. So this is the diagram of leakage reactance in primary and secondary. So leakage results in energy being alternatively stored in and discharges from the magnetic fields with each cycle of the power supply. It is not itself directly a source of power loss but results in poorer voltage regulation, causing the secondary voltage to fail to the directly proportional to the primary particular under heavy load. So distribution transformers are therefore normally designed to have very low leakage inductance. So here is the practical transformer with winding leakage reactances. So it has the X1 and X2 reactances. So in this effect of leakage reactance in primary and secondary winding, the leakage flux linking with each winding produces a self-induced EMF in that winding. Hence, the effect of leakage flux is equivalent to a small inductive coil in series with each winding. The reactance of this inductive coil The reactance of this inductive coil is known as leakage reactance. In other words, a transformer with magnetic leakage is equivalent to an ideal transformer with inductive coils connected in series with each winding is in shown in diagram. So the leakage reactance of primary and secondary windings are X1 and X2 respectively. The leakage fluxes inductive self-induced EMFs in their windings which opposes the flow of current in their respective windings. Therefore, the primary reactance can be obtained by dividing the self-induced EMF by the primary current, and the secondary reactance can be obtained by dividing the self-induced EMF by the secondary currents. So, the leakage flux linking with each winding produces a self-induced EMF in that winding. Hence, the effect of leakage flux is equivalent to a small inductive coil in series with each winding. The reactance of this inductive coil is known as leakage reactance. In other words, a transformer with magnetic leakage is equivalent to an ideal transformer with inductive coils connected in series with each winding. The leakage reactance of primary and secondary windings are X1 and X2. It will be shown in the diagram. The leakage fluxes include self-induced EMFs in their windings which opposes the flow of current in their respective windings. Therefore, the primary reactance can be obtaining by dividing the self-induced EMF by the primary current, and the secondary reactance can be obtained by dividing the self-induced EMF by the secondary currents. So the writing the KVL equations for the primary and secondary loops, we have primary induced EMF E1 is equal to V1 minus J I1 X1, and similarly secondary induced EMF E2 is equal to V2 plus J of I2 X2. So here reactance transfer. Looking into the circuit from source side, let us define the impedance as X in is equal to V1 I1. Looking into the circuit from load side, neglecting the load itself, let us define the impedance as XL is equal to V2 by I2. Relating V1 by I1 in terms of V by I using the turn ratio, A V1 I1 is equal to A square V2 by I2. So that is equal to X is equal to A square XL. Hence, in general, any impedance transferred from secondary side to the primary side must be multiplied by the square of the turn ratio A square. So the leakage reactance of secondary referred to primary, that X2 dash is equal to X2 by K square. The total leakage reactance referred to primary, X naught 1 is equal to X1 plus X2 dash. Similarly, the leakage reactance of primary referred to secondary, X1 dash is equal to X1, that is equal to K square into 1. So the total leakage reactance referred to secondary X naught 2 is equal to X2 plus X1 dash. So this is the effective reactance in primary circuit. So here the primary leakage reactance X1 is equal to EL1 by I1 ohm, and secondary leakage reactance X2 is equal to EL2 by I2 ohms. In primary voltage, V1 will have to supply the reactance drop I1 X1 in addition to I1 R1. Similarly, induced EMF V2 will have to supply reactive drop I2 X2 in addition to I2 X2. So equivalent leakage reactance, uh, equivalent leakage reactance. So this is the X naught 1 is equal to X1 plus X2 dash. So in this equivalent leakage reactance, the transformer with the leakage reactance and in the primary and secondary winding respectively, similar to that of the resistance, the leakage reactance of one winding can be transferred to the other winding by using the factor K square, means K transformation ratio. This means that both the reactances can be transferred to either primary or secondary, which helps in finding equivalent reactances on either side. The advantage of transferring the reactance to one side, that it makes calculation simple and easy, because then we have to work in one winding only. So this is the transformer with both winding resistance and reactances. So in reactances, it is will be referred to in primary when secondary leakage reactance is transferred to the primary side. It is divided by K square, then it is known as the equivalent secondary reactances referred to primary and is denoted by X2 dash. Equivalent secondary reactances refer to primary, X2 dash is equal to X2 by K square. When the secondary reactance is transferred to primary side, then the secondary has no reactances. The leakage reactance is x1 plus x2 dash, that is equal to x1 plus x2 by k square, is known as the equivalent or effective reactance of the transformer, referred to primary, and is denoted by x naught 1. It is denoted by x naught 1. Equivalent leakage reactance referred to primary, x naught 1 is equal to x1 plus x2 dash, that is equal to x1 plus x2 by k square. Same as referred to secondary side, when primary leakage reactance x1 is transferred to the secondary, it is multiplied by k square, then it is known as equivalent secondary reactance referred to secondary and the denoted by x1 dash. So equivalent primary leakage reactance referred to the secondary, x1 dash is equal to k square x1, k square x1. So when the primary reactance is transferred to primary side, then the primary has no reactance. The leakage reactance x2 is x2 plus x1 dash is equal to x2 plus k square x1, is known as the equivalent or effective reactance of the transformer, referred to the secondary, and it is denoted by x naught 2. So equivalent reactance, equivalent leakage reactance referred to secondary, that is equal to x naught 2 is equal to x2 plus x1 dash, that is equal to x2 plus k square x1. So here, so it is the effective reactance in primary circuit. So here x naught 1 is equal to x1 plus x2 dash. So this is the transformer with both winding resistance and reactance. In this resistance and leakage reactances of the primary and secondary windings. So in primary side it has the R1 and X1, and it has the current I1, voltage V1, and E1 EMF, and is the number of turns in one. So the maximum flux is common in both windings, and in secondary winding it has the N2 number of turns, and E2 mutual induced EMF, and it has the X2 reactance and R2 resistance. So in this has the I2 current and load Z, and also it has the V2 voltage. So in this resistance and leakage reactances of primary and secondary. So in this the impedance Z, Z1 is equal to R1 plus JX1. Uh, it is the primary impedance, and the secondary impedance Z2 is the R2 plus JX2. So it is the primary and secondary impedances. The impedance of the primary winding is Z1 is equal to R1 plus JX1. Similarly, the impedance of the secondary winding is Z2 is equal to R2 plus JX2. So here, therefore, the voltage drop in the primary winding. Therefore, the voltage drop in the primary winding is due to its resistance and leakage reactances. Hence, V1 is equal to E1 plus I1 into R1 plus JX1, that is equal to V1 is equal to E1 plus I1 Z1. Similarly, in the secondary winding we have E2 is equal to V2 plus I2 into R2 plus JX2, that is equal to, these are the vector sums. Vector of V2 is equal to vector of E2 minus I2 Z2. So the uh, resistance referred to primary R01 is equal to R1 plus R2. So total reactance referred to primary X01 is equal to X1 plus X2 dash, that is equal to X2 dash is equal to X2 by K square. Total impedance referred to primary or Z01 is equal to Z1 plus Z2. So that is equal to Z01 is equal to R01 plus JX01. So total resistance referred to secondary R02 is equal to R1 dash plus R2, where R1 dash is equal to K square R1. The total reactance referred to secondary, where X02 is equal to x1 dash plus x2, and x1 dash is equal to K square x1. Total impedance referred to primary or Z naught 2 is equal to Z1 dash plus Z2, that is equal to Z naught 2 is equal to R naught 2 plus J X naught 2. So in this the transformer primary leakage reactance to secondary side, multiplying it with k square of means x1 dash is equal to K square x1, and to transfer secondary leakage reactance to primary side, divide it with K square. So that is equal to x2 dash is equal to x2 by K square. So this is the uh, leakage reactance in primary and secondary. So in summary, we have discussed about how a real transformer with winding leakage is represented, and the transformation of magnetic leakage into the equivalent reactance, the derivation of the formulae to transfer reactance from one side to other side, and the representation of real transformer with both resistance and leakage reactances. And also we discussed about how a real transformer with winding resistance is represented, and the phasor diagrams of the transformer at different loads, visualizing unity power factor, lagging and leading power factors, considering the resistances of the windings only. The derivation of the formulae to transfer resistances from one side to the other based on equal power loss. So it has the frequently asked questions. So in this it has the one problem. A 33 kVA to 2200 by 220 volts 50 Hz single phase transformer has the following parameters: R1 is equal to 2.4 ohm, X1 is equal to 6 ohm, R2 is equal to 0.03 ohm, X2 is equal to 0.07 ohm. Find the primary resistance and leakage reactance referred to secondary, and the second bit is the find the secondary resistance and leakage reactance referred to primary, and find the equivalent resistance and reactance referred to primary. And also in frequently asked questions, second is the derive the relation for equivalent impedance of the transformer when referred to primary and when referred to secondary. Explain with neat sketch. What are the effects of winding leakage of the transformer, and explain the necessary of transferring impedances from one side of the transformer to the other, and also derive the relation for equivalent resistance of a transformer when referred to primary and referred to secondary. Explain with the neat sketches. Draw the phasor diagrams of the transformer for resistive and inductive loads, assuming the winding have only resistances. And also we have, what are the effects of winding resistance of a transformer? Explain the necessity of a transferring resistances and impedances from one side of the transformer to the other. So these are the few frequently asked questions, and in next class we go for the transformer with resistance and leakage reactances. So this is the today's topic. Thank you.